Okay, yeah. So I suppose this talk will serve different people in different ways. But I guess in general, everybody ought to leave here knowing what the heat equation is, knowing a couple of ways to solve it in one dimension and in two dimensions. You'll have a better familiarity with a number of Python libraries that you may or may not know already, and you should be able to generate some nice animations of your solutions. So these are our objectives. Right? Okay. Why Python for this? Tristan Needham wrote a really great complex analysis textbook called Visual Complex Analysis, and he opens the book with this quote saying, math doesn't really change, but computer science changes. So it's easy to learn how to solve the math equation in principle, but then you need to choose a proper platform to do it on. And I want to suggest that Python is a good language to do it in, because for a number of reasons, Python, the portion of Python that we're going to use today looks remarkably like MATLAB. So if you're used to doing this sort of thing, you've probably done it in MATLAB. So it'll be really easy to rewrite it in Python. It'll look almost exactly the same. In addition, once you learn how to do this in Python, it'll really, now I suppose everybody here already knows Python for a number of purposes, but for the folks that maybe come here just for science or just for mathematics, Python opens the door for you to do much more programming than MATLAB will ever let you do. With MATLAB, you can solve the heat equation and that's it. But once you know how to solve the heat equation in Python, you can do so much more. Right, so this is a good language to do it in. Also, it's been around. MATLAB came out in 1984. The first version of NumPy came out in 1995. So they've both been around a while. They're both very good. They're both very reliable. So there's nothing wrong with it. The libraries we're going to use today is, we're going to use a scipy stack. I guess I'm just going to say it and assume that not everybody here knows it. So if you all are familiar with all this, I'm sorry that you got to go through it. But we're going to use the scipy stack, or a portion of it. We're going to use the scipy core library that has a number of linear algebra functions that we need. And then this is how we're going to store our matrices that we're going to use. We're also going to use NumPy. This is where we're going to get our arrays from to represent our vectors and whatnot for the equation. We're going to use Matplotlib to make our animations and to make our graphs. And IPython, I don't think we're going to get to use that today. I hope to do everything in IPython notebooks, but I think that's maybe a different talk for someone else to do. So we're not going to use that. We're just going to write scripts. All right. And yeah, and if you have any further reference, you can head over to Thompson and find something there. That's a joke, because that's a library here. Okay. So to get all this stuff that we're going to need, I don't know, perhaps you don't have it installed already. I just went to the SciPy conference in Austin a couple weeks ago, and it was amazing. And I met some folks who have made Anaconda and nthought Canopy. These are like two distributions. They have the whole SciPy stack and a whole bunch of things that we're not even going to use today, but that you might use in the future. So in general, we need any version of NumPy will work for this talk, provided you don't have something from like 2002, but anything from 1.6 or so and on will work. Matplotlib, you need 1.3, that'll work. And SciPy, get the newest version, I think it's 14. But in general, if you want to just get around all that, you can just install Anaconda or nthought Canopy. And if you just Google this, Anaconda SciPy, it's there, it's the first thing that'll come out. If you don't have it already, I mean, I recommend getting one of these two. I haven't used nthought Canopy, but I've heard it's great. I just use Anaconda because it has everything there, and they have their own version of like a pip kind of thing to install some stuff. So whatever you might need in the future, you can install it from there as well. So if you don't have like NumPy, SciPy, Matplotlib installed right now, I would suggest that you get one of these two right now. And then over the next 15 minutes or so while I talk, I don't know how slow the internet is here, but it ought to download and then be working by that time. Right. So either one of them is very good, and I don't know the website off the top of my head. I didn't put it down. I think it's anaconda.org or something like that. But if you Google Anaconda Python or nthought Canopy Python, it'll be the first one there. If you click on the link, there'll be a download link there, and you can get it. And if you have, they both work for Windows, Mac, Linux. It'll work for any one of those. If you go on the SciPy website, they'll suggest a laundry list of different ways to get all these things. And I would say don't do any one of the other ways that they suggest, because Well, because these work on, if you have Mac, Linux, Windows, it'll work. And if you get one of the other things, I don't know, you may get like tar balls or something like that. That'll be a little more work. This will just be, just click download and it installs for you. So yeah, one of these is great. Okay, so, all right, so getting to the problem now, we're going to solve the heat equation. We're going to start by doing it in one dimension. So the idea here, the problem that we're going to solve is we have a one-dimensional pipe, a bar or something like this. It's a uniform density, okay? It's a homogeneous material, right? It's just a long pipe. It's solid, okay? And we're going to heat it up in some way. We're going to give it some initial temperature distribution, okay? So something like this exhaust manifold, right? We're going to heat it up in some way that, you know, it'll be, it's a pipe on two ends. We're going to talk about the two ends of the pipe later, but for now we can just keep in mind we have a pipe. It's uniform throughout. It's insulated along the whole length of it, except at the ends, because we're going to play with the ends. We're going to do some stuff to it, and that's going to change the temperature in the pipe, right? Because we want the temperature to change in the pipe, otherwise this would be boring, right? Okay, so that's the idea. It's not going to be as interesting as this, though. We're going to have a flat pipe, insulated, so there's going to be no interference from the outside, right? Just on the ends, right? Okay, so good so far. Okay, great. Okay, so now we're going to talk just briefly about the math behind it, right? There's a differential equation that would describe the way that the temperature in the bar changes. It's called the heat equation. Okay. But that's a continuous equation. So we're going to have a bar. The bar is continuous, right? There are infinitely many points on the bar. Okay. Or it's not. Yeah. So there are infinitely many points on the bar, but of course we can't handle that, right? I may have misspoken, but that's fine. We can't handle every point on the bar, so we're just going to take a number of them. So we're going to discretize the bar, right? We're going to take just a handful of points, evenly spaced throughout it, and we're going to see how the temperature changes at these distinct points, right? Okay. I don't mean to belabor it too much, right? But I want to make sure it's clear, right?
Is that really necessary? I thought the heat equation actually had not an exact solution, expansion and Fourier series that you could do as to whatever accuracy you wanted without having to do grids and discrete whatever.
Yeah, you could do that, and there's definitely, you could get sometimes. Well, there is an exact solution of it, but the method that we're going to use will handle any equation. Well, we're really simplifying it, right? There's so much to say about this problem, right? We could talk. This could be like a 2-semester course, right? So we're going to really simplify it, right? Yeah. So yeah, there are many ways to solve it, right? But we're going to focus just on this way, just because there are lots of equations that you solve in the same way with finite difference methods. So this is a good entry point, I think. Yeah. So this is the equation. It's we have u is a function of x and t. Okay. So u is a function of x and t. The u is the temperature in the bar, and it varies depending on your position in the bar and on how much time has passed since your initial heating of the bar. Okay. Yeah. So u is a function of x and t, and it varies. Yeah. So it depends on x and t, and u is the temperature in the bar, right? And this is the relationship we have, and we're not going to derive this. We're just going to accept this as true, okay? That the derivative of u with respect to t is equal to the second derivative with respect to x, all right? And we're not going to talk about why. It just is. So we're going to discretize it. And I think I said in the pamphlet that all you need to know are derivatives. Okay, so this is pretty much the extent of it. The derivative of u with respect to, and let me, before I even go into this, if this looks intimidating at all, that's totally fine, right? That's totally fine. We're going to have a code that runs, and soon we're going to modify it together. And if this is somewhat confusing, I wouldn't worry about that at all, right? I mean, once, if you're just an excellent Python programmer, you'll get through this anyway.
My keyboard doesn't have that triangle, but that's okay.
Yeah, I mean, yeah, you may need like a LaTeX thing or something like that, right? But yeah. Yeah, that works too. Right. The Greek language pack or something like that. Okay, yeah, so again, so just in general, we'll just spend a minute on this. The derivative with respect to t is going to be the change in t, the change in u with t over the change in t, okay? Yeah, so I guess if this isn't immediately clear, I wouldn't worry about it too much. And then the second derivative is a little bit more hairy to explain, I guess. So we'll just accept that as true also. So this is the equation. This is the discretized version of the equation. Okay. And then we're going to rewrite it. All right. We're going to bring that delta t over here, put it there. And then we're going to bring this here over here. Minus change the plus, right? Okay. Any questions so far? This is good? This is good? Okay, great. Okay, and then we're just going to change our notation a little bit, just so this thing doesn't wind up taking, and we're going to do this in 2 dimensions in a minute also, or in about an hour. So in 1 dimension, this is already nasty to look at, and in 2 dimensions, if we don't change our notation, it's going to be awful, right? So we're just going to say u at x and t is going to be ij, and x minus delta x is going to be I minus 1. And then naturally, if you have x plus delta x, which we have over there, okay. So this would be ij, and if we have x minus delta x, we'll just replace that as I minus 1, and the t is still going to be j, okay. And then anybody want to volunteer? Then this one, we would represent this with u, what subscript? Yeah, okay, j, right? Great, okay. So just want to make sure that's very clear, right? Great, okay. It may seem trivial, but yeah. And then we'll just replace this delta t over delta x squared by an r, so we don't have to write, because I don't even have this on my keyboard either, and it was taking me forever trying to figure out a way to write it. Right? So we just write r, okay. And then the point of this is, so we know something about u at some time t, okay, at some time j, and then we're going to use this information to figure out something about u at time j plus 1. So that's the essence of it. We know something about u at some time j, and then we're going to go forward to some time j plus 1 and know something about the, all right, so say we know the temperature in the bar right now, and we want to know how hot it's going to be in 20 minutes. We can just do this a bunch of times, all right, because we'll know at j, we can go to j plus 1, j plus 2, j plus 3, j plus 4.
Is interested in that top line. What it actually is you're taking 2 points, one at t and one at t plus 1, drawing a straight line between them, getting the slope.
Yeah.
The second, on the right-hand side, it's taking x, then x plus something, x minus something, drawing a parabola between them, and taking a slope at the middle point. And that's all that really is.
I had considered just starting this from slopes, from y equals,
Well, a double slope.
yeah. I'd considered starting way back though, just with slopes, with m equals delta y over delta x, and then going into a derivative and then throwing away the limits and whatnot. But then I thought that's going to take 30 minutes. So we're just going right with this, right? Okay. Yeah, so again, so if you understand this part, this is all we really need to know to code up a solution, right? So again, remember this. This is the main idea here. This is going to be how we write this code. Okay. Yeah, underlying this, we have a concept of some mesh that we're using. Okay. So this looks, there's a lot of, so I went to a talk a while ago and there was a guy and he was giving a talk about how people when they teach, they shouldn't always make their own teaching materials, because for something like this, like the heat equation, like how many times does someone need to draw a mesh here and spend 20 minutes of their afternoon doing this? He said, why don't people just share these? So I went on his website and I stole his mesh, but it has some extra information in here that we don't really need. So just ignore these fractions here. The idea here is we have our y-axis. This is going to be like our x, okay? This is going to be like the bar, which we cut up into a finite number of intervals, okay? And then our this axis, our y-axis, or our j-axis in this case, this is going to be our time steps, okay? So we're going to start out with some at time 0. We're going to know something about u at these finite number of points. And then we're going to use that equation that we just saw, and we're going to go to the next one. And then we're going to know something about it there, and then we're going to go to the next one, and then the next one, until whatever we wanted to end. And we could do this as long as we wanted to, right? Provided we wrote this code correctly, right? So I guess the idea is, if you remember, we're using u ij, and u I plus 1j, and u I minus 1j, to get to u ij plus 1, okay? So if you ever look in a textbook or something like this, you're going to see this picture, right? We're going to use these 3 points here in the mesh to go here, right? So, for example, if we want to go to this point, we're going to use these 3 points, and that'll take us there. But I don't know, you may already notice, we're not going to get to it. We're going to get to it in a few minutes, right? But there's going to be 2 issues with this mesh. But I'll just say it now. I mean, we have an issue here, and we have an issue here to get to here, and to get to here, right? If you don't see it, it's because we're using these 3 points, and that one's falling off the end here, and the same on the other end, right? So we're going to propose a way of dealing with that in a minute, all right? Okay. And then here's a different mesh if you didn't like the last one. This one's from UC Berkeley, so it's legit. It's very good, right? This is just another way it's less cluttered, right? We have these 3 points here, and we're going to take those to get to the next one, to the next. Yeah. So again, this is our bar, and this is our time. And then we're going to have some solution here. We're going to have some solution lying here, and then some solution here, and so on to the end. Right. Okay. Any questions so far? We're almost done with the math part, so I want to make sure it's clear. That's good? Okay. Again, this is important. This is the main idea. Right.
So, in really plain terms, what you're saying is, in the next time period, the temperature of a segment is depending on its previous.
Exactly right.
Or and its 2 neighbors.
Yeah. Yeah, exactly right. Okay, so there are going to be a number of boundary conditions. So I said that we have these 2 issues on the ends, okay? So those are going to be like our, what we call our boundary conditions, okay? The first one we're going to look at is we're going to have some constant boundary conditions, where we're going to heat up our bar, and we're going to put some kind of igloos on the end of it so it stays nice and cold at the ends, okay? We're going to keep it at a constant temperature, cold at the ends. This is one way that we could deal with this. Of course, it depends on the problem at hand, right? Yeah, so we're going to keep the ends of our bar constant in this case, and you don't see it, but this bar is insulated along the whole length. The other thing that we could do is we could have maybe some function that governs the temperature at the ends. Maybe it doesn't have to be constant. Maybe it doesn't have to have these 2 cold igloos on the end, right? You could have a thermostat on the end that you play with, in such a way that the temperature on the ends changes, right? So, yeah. So, and we could also mix it, right? We could have an igloo on one end and a thermostat on the other one, right? All right. So, and there are many other types of boundary conditions as well, or a couple other ones, right? We can mix these. We could have derivatives on the boundary. We're not going to do that because that might take a few more minutes. So we're just going to deal with either constant boundary conditions or some function on the boundary. Okay. Okay. Great. Now we're going to make a matrix equation out of this to make this compact and easy to solve. All right, right? Or whatever we're going to. So we don't have to go through. So we're going to have a lot of these equations flying around. We're going to want a nice, neat way to represent them. Again, this is the equation we're trying to solve, and we're going to use this we're going to use this matrix. And I don't know if any of you are into like graphics programming. I guess you're like monsters at linear algebra, right? But maybe some of you write like web apps or something, and maybe you don't need it so much, right? So we'll just review it really quick. I want to make sure this makes sense to everybody. We can ignore the first line here, and we can ignore the last line for now, for 1 second. So, like you were saying before, right? If we know, we're going to use. Let's look at this, for example. I meant to put a j+1. I did this when I was sleepy about a week ago. I'm sorry. This is supposed to have a j+1 here. Oh, no, it's not. I'm sorry about that. I misspoke. That one I threw away. Yeah, so, okay, I'm sorry about that. Let's just multiply these things for 1 second, and then we'll talk about what this means. If we multiply this matrix by this column vector, does anybody want to shout out? Let's multiply this row here over here. Anybody want to shout out what we would get? If anybody remembers, and if not, I'll just tell you, right? Oh, sorry. Yeah. Yeah, great. Okay. So that was like, yeah, a lot of people know that's good. Anybody who doesn't know, if you're gonna multiply this, I don't know. When I took this linear algebra class a long time ago, and the first time I heard it, my professor, he said for the kids in class who don't understand, he just went like this. He put his hand here, and then he went like that. And he said, that's what you're doing. You're taking this, and you're multiplying it by that. And I don't know, for some reason that stuck in my head. And there are millions of ways to talk about this, but just for the sake of the next hour, right? If you get confused, you're gonna take some row here like this, and you're gonna stick it on top here, right? So we're going to multiply the 1 there, and we're sticking it here. We're going to multiply the 1 by this. And the -2, it's going to go on top of this, and we're going to multiply it by that. And the 1 here, we're going to multiply it there. And then the 2 zeros will go there. Then we're going to add those things together. Okay. And we'll do this once more. I see some glazed eyes. So we'll do this once more to make sure it's clear. Right. So this one, we're going to multiply the 1. We're going to take this row and multiply it here. We're going to get a 1 times this one. Well, that'll go there. We'll get a -2 times this one. That's right there. We'll get a 1 times this one here. That's there. And then there's 2 zeros. I didn't bother writing them because that's just going to be +0 and +0. Okay? Right. And then the same. Now, the issue is these two, there's no 1 there, and there's no 1 over there on the end. So we're going to need, if you remember, oh wait, it's right there. We need this for all of them, but we said on the boundary that there's going to be an issue. We need this equation everywhere. So for this one, we're going to need this. Say we wanted to solve for u1j plus 1. We're going to need u0j, right? But we don't have that here. We're going to. This is just one way of representing it in a matrix. I just chose this one. There are a couple of ways. I just happen to choose this one, right? Because it's quite popular. We're going to see that we're going to have to add another, we're going to need to add something else over here. We're going to need to add a U0 here, and we're going to need to add a U6 here to make sure that all of these look like this. Okay?
So are you just doing this as linear algebra review, or is that matrix on the left actually coming from some data?
Yeah. So this matrix on the left, in case it's, this matrix, this is going to be our matrix equation for this, right? So by just multiplying, we're going to have our bar, our vector that has all the data points in the bar in it, and we're going to multiply this matrix by that vector, and that's going to take us to the next time. So, well, we're going to need to put a little more seasoning on it, right? We need to multiply this by r also, and then we're going to need to. So this matrix is representing this part here, right? For all the points, right? For all the points, it doesn't, right? Instead of writing all these different equations, we just have one matrix or an array, depending on whether we're using numpy or scipy. And so that way it saves us from having some nasty for loop that runs forever and ever and ever, right? Okay. All right, so finally, okay, sure. Let's look at some code together then. Okay. Before we do that, I had the issue of distributing this code to everybody, so that I pretty much wrote a template of a code, and the idea here is I give you one that solves the equation in a certain way, and then your part here in a few minutes is going to be to change this code so it does something a little bit different, right? To make sure that you really understand everything that's going on. And I'm going to show you one way to make an animation, another way to make an animation, another way to make an animation, right? And then you're going to have to create your own animation of something else, right? That's related to this, right? But then I had the issue of distributing this code, this template to everybody. And I didn't know how to do it, and I was going to put it on like GitHub or something, but then I figured half people use like Subversion or something like that, and then so I didn't know what to do. So I figured I would just have you all send me an email, and there are more people here than I expected. I figured everybody just send me an email, and then I could shoot you an email back that has the folder, the code in it. And it's very small. It's like 10 megabytes or something like that. So does that sound good? All right. Maybe my email is this is the best way I could figure to do this. So my email is I will write it here, and I hope I don't get. I use this editor. I hope no one here wants me to use Emacs or something. It's called Genie, and it's really great.
If you like it, that's what matters.
Yeah, right. I mean, I think so too. Like the Vim and all that was giving me a headache. The Emacs was worse. No thanks. Yeah, so this is my email. So if you wouldn't mind, this is really small. That's my email. And if you want to shoot me an email, then in the next few minutes I will send you one back that has all these codes in it that we're going to talk about now, so you can modify it yourself. Right? Okay. All right. Okay. All right. That's pretty short, so I'm going to assume everybody's seen it, and everybody who wants it has it, right? Okay. Okay. So the first one we're going to look at is this. So this code here is going to solve the equation with constant boundary conditions. This one's going to be like the equation that has these igloos on the end that we talked about. Okay. So does everybody here use numpy or scipy? Does anybody not? Okay, great. I just assume somebody does not. So I'm just going to start from the ground up, okay? Right. So, and I don't even know if you'll use Python or not. So I'm just going to start really low, right? Okay. From the top, we're just going to import, I don't know, maybe if you're like a C programmer or something like that, you want to have some includes or something, right? Something like that. We're importing a few things from NumPy that we're going to use here. We're going to need some arrays. We're going to need a dot product. Or NumPy, if you want to multiply a 2D array by a 1D array in NumPy, you use the dot function, okay? Instead of like, if you use MATLAB, you can just put a star, right? In NumPy, you have to use dot, right? And we need, we're going to make diagonal matrices, which we saw before. So we need a diagonal matrix. And we're going to need to be able to make vectors of, or arrays of zeros and ones. So I imported zeros and ones. Okay. This function solves a heat equation, and it's going to use what's called the forward Euler method. Okay. So what we're going to do is we're going to start at some time t0. We need to know what our step size is in x. So we're just going to take our x array and find the distance between 2 points, which is just the first point minus the second point minus the first point. That difference is going to give us a spacing between points. Excuse me. And we're using a uniform spacing, so this is good. Okay. Okay, we need to figure out. We're solving we're assuming that there's a constant temperature on the boundary, so we're only solving for the length of our initial array minus 2, because we don't need the 2 on the boundary. So I just threw those away. So that's what the minus 2 there is for, because there's the number of elements in our initial temperature minus 2. Okay, is that clear? Is it not clear? Okay. We saw before R is dt over dx squared, so that's exactly like what we saw before. Okay. In our matrix, if we remember, the main diagonal had -2 on it, so we made our main diagonal, it's going to be, I made 1s on it and then multiplied it by -2, okay, because there's no -2's function, okay. And then off the diagonal, above the main diagonal and below it, if you remember, there were 1s, okay? So that's what this is. We have 1s there. And then I made a little function that would make a tridiagonal matrix using these two. This has 1 less because the main diagonal will have, say, n elements on it, but then above and below, it'll be short 1, okay? And if you don't believe me, try to visualize it for 1 second, right? If there are like 5 on the main diagonal, above and below, there will only be space for 4. Okay, so there's a -1 there. I don't know if anybody here is really good at NumPy, and if you are, if you would tell me, that would be great. So far, I don't know any way of making a tridiagonal matrix without writing a quick little function to do it, and it's only, a couple of lines, so it's not really a hassle, but it's just adds a couple of lines, and it seems like something that a lot of people would want to do, right? So perhaps we could even contribute this to NumPy, right? And then we're going to let you, okay, so now we're going to start our integration right now. We're going to start solving right now. We had some initial condition here, and now we're going to say our current temperature on the bar is U, and we're going to set it equal to our initial condition. So now we're getting ready. Now we're starting to go, right? Now we're starting to solve it. Oh, one more step though. Sorry. If you remember that matrix that we saw before, the -2, 1, 1, -2, 1, the 1, -2, 1, that one, there was an issue that when we multiplied it, we were missing the boundary elements in there, right? Yeah, so we were. And if you didn't catch that part, I'm trying to talk slow, but I imagine that this may be a lot to take in at once, unless you've seen this 1,000 times before, in which case this is boring, right? But if you haven't seen it before, you may be sweating a little bit, right? So I'm just saying, if you think back, there was a matrix. In that matrix multiplication example, we were missing the boundary conditions. So we're just going to have to make a boundary condition vector here. It has zeros in most of it, except the first one is going to have to be the first element from our initial condition array. And the last one has to be the last one from our initial condition array. And then in between, it needs to be zeros. Because in between, the matrix multiplication worked out fine, right? If you remember, it looked beautiful. It was exactly what we wanted. But then on the ends, it wasn't good, right? So we're going to have zeros in most of our boundary condition vector array. Except at the endpoints, we need to take care of that. Okay. And now here, this is the main idea. Now we're going to solve it. No, the way that NumPy does array indexing is a little bit confusing, I think, the first time you see it, and maybe the second time, but then after that, it's very clear. We're only going to want to update the elements on the interior of the bar, correct? Is that right? Because the boundaries they're fixed, right? So this is going to be how we're going to access the interior elements. And then, so yeah, Python arrays start at 0, just like C. But if you're in MATLAB, I think they start at 1. So maybe if you were just to take your MATLAB code and rewrite it, you may get frustrated and stop working because it wasn't working. But it's just the indexing is different. But then you also might say to yourself, how come here the last element from here is -1? But then in here, we don't want the last element, right? We're not updating the last element in the U vector, right? Because again, we said it's constant, right? But then here, if we look here, we're putting the last element from the initial condition here by putting -1. But then here, our index is going up to -1, and you might say to yourself, that looks bad, right? Does that look bad to anybody? It looked bad to me the first time I saw it, because this looks like we're including the last element. It looks like we're starting at 1, which is the second element, right? The first element is 0, right? The second element is 1, right? So we're starting there, but then we're going up to -1, or so it seems, right? But we're not going up to -1. We're going up right before the memory address of -1, which is awful to think about, right? But it works fine. Once you see it twice, it's fine. We're going right, -1 is here, and we're going right before it. And that just so happens to be here at -1, okay? There may be a more eloquent way of saying it than that, but that's the main idea. So if we're just using an index, we'll use -1 to be the last element. But if we're accessing multiple elements, we're just going to go up right before -1. Okay. So now, yes.
Because I also don't know so if you want to do it on the last one.
Yeah. So this is the last one. You plug in -1. But if you want everything up to the last one, and say you're indexing some range of values, you're going to go from whatever you want, and then you're going to put here ahead of what you want, right? Because the last element will be -1, so you're going to put that there. That's ahead of what you want, right? You don't want to go there. You want to go up to -2. Well, if you put -1 there, that'll take you up to the -2 element. Okay. Okay. And I saw there was I think it's on YouTube. There's a 2012 Introduction to NumPy and Matplotlib talk by someone named Eric Jones. And it's amazing. And it's like 2 hours. So I don't know if anybody's really interested in this and you want to get really proficient at it. It's a wonderful tutorial. He explains this in great detail and also plotting in great detail. It's really long, but you can play it at 2x speed and get through some of the slow parts. Right. Okay, so again, so our u at time j plus 1 is going to be the u at time j plus r times the product of some matrix T, which we made here with this make tridiagonal matrix function, times the inner elements in the vector, right? Plus our boundary conditions, right? Because we needed to add the boundary conditions to it as well. All right. So is that. And then as we loop through this, however many times we want, a number of times, you're just going to have to increment time, right? Because when you return from this function, you want to return the time. You don't want to return the initial time, right? You want to keep incrementing the time. Okay. So this will be the value of u at time t plus dt. I suppose I think it's better to minimize rounding error to use multiples here instead of adding dt every time. So in case anybody's offended by that, in case anybody's done this before, I think a lot of people will be offended by me just adding dt every time we loop through. Someone would prefer there to be like a j times dt or something like that. And if that sounds like Chinese to somebody or whatever, maybe. Say that again?
Step times.
Oh. Like here, I think.
The loop variable is step.
Yeah. Mm-hmm. Yeah, we don't really need step.
Oh, right.
Yeah, I'm just incrementing time. Yeah, we could have like step times dt in here, right? And that would like I think you get the rounding errors are worse if you use addition than if you use multiplication, because there's gonna be a lot more of them, right? You're gonna do every time you loop through this, you're gonna do another addition, and you're gonna lose some precision every time. But if you use a multiple here, you'll only lose that precision once. But again, that may be confusing to look at, and this is very obvious to look at, that every time we loop through it, the time increments by dt. All right, and then after we run this function, we're going to want to return u, and we're going to want to return time. Okay.
One question.
Yeah.
I thought you had said at one point that there was something we needed to do for the end calculations.
Yeah.
Because we didn't have points beyond whatever.
So exactly. So in this example, right? This is our starting, right, here. We're gonna change only the interior parts of u, and the exterior parts are not changing. U is not changing on the end. We're just leaving that how it is, right? Because here we set u equal to u naught, to the initial u. So we're only updating the middle parts. So the endpoints are not going to change. So when we return u here, it's going to have the same endpoints as the initial one, right? And that's good. But later, I'm going to give you the task of writing this that has a function on the boundary. It's going to take a slight modification. Slight, right? Somewhat small. But yeah. So and then in case anybody wants to see make a tridiagonal matrix, I would like to talk about this in some detail in a minute. Again, there's no function in numpy to do this, which is a shame because there are so many times you need to do this for finite element codes or finite difference codes. You oftentimes need these tridiagonal matrices, and there's no way to make them in there. But yeah, so anyway, so this is going to give us I wrote make tridiagonal matrix because I was writing it like the math part. This is going to be a tridiagonal ND array or 2D array. So in this example, we're using numpy arrays. So this is going to give us a diagonal numpy 2D array. Okay. We're going to give it some array to place along the main diagonal. And if you remember, we made that up here, right? The main diagonal was -2. Okay. So we're going to put that there on the main diagonal. And then I give it some. Now this one just happened to have the same on the sub and super diagonals. It has ones, right? So I just only give it an offset 1 array here because it's going to be the same on both of them. But suppose you needed a 1 on the super diagonal and a -5 for some reason. On the sub diagonal, you would need to pass us another parameter, right? You could give us like a sub diagonal parameter here and then a super diagonal parameter also, right? But in this example, the sub and super diagonals, they're both 1s. Okay. I only passed it, so this is going to go on the main diagonal. and this is going to go on the sub and super diagonals. And it just so happens that in this case they're the same. But again, if they were different, you could just pass another parameter here, and then in here you could, yeah. So let's go in here now. Now we're just going to create we're going to do a sum here of 3 diagonal arrays. We're going to have the diagonal array that has whatever we said main was on the main diagonal, and then whatever we said offset 1 was, which in this case is going to be what are we placing on the offset 1? Just to make sure everybody's with me. 1s, yeah, right? 1s, okay. And that's going to be on the -1 diagonal. That's the sub-diagonal, okay. And then when we set k equals 1, that's going to be the super diagonal, right? And it's going to have the same value, offset 1. We have a sum here, and if you would have, so these arrays, you have to be careful with them. We had to make sure that 1s was 1 less than the number of unknowns. I said that before, because if it wasn't, this diagonal array would have dimension, say, n by n. But then this one, because this is on the subdiagonal, would have n plus 1 by n plus 1. Okay. If that doesn't make sense, just, I'm going to give you this code. Get rid of this -1 here, and you're going to get some kind of error. Because this array is going to be too big, and this array is going to be too big. You won't be able to add them. The dimensions need to agree. Okay. Okay. And now, last but not least, we're going to see how to run this thing. Okay. Now, if you're a MATLAB user, this is going to look fairly straightforward, with the exception of maybe 1 or 2 parts. Okay. Again, we're going to have to import some things. I meant to change this. From NumPy, we're going to import E, Euler number. We're going to need linspace, which gives us a vector of evenly spaced, or an array of evenly spaced points in some range. We need pi in here. Vectorize is another cool function, which we actually don't need. I did this one a while ago. I meant to delete it. From here, let me get rid of this. I'm sorry about that. From math import sign, I saved the wrong one here. We're going to want to import sign from NumPy. Okay. There's a sign function in math, but that one's not vectorized. But sign in NumPy, you can pass it an array, and it'll do sign of all the array elements. But if you give the math sign an array, it'll give you an error message. Right? It's not vectorized. Okay. Okay. Again, if you're new to Python, if you're not new to Python, this is trivial. If you have some other script somewhere and you want to import some functions from it, you just say from whatever the name of that script is, import. You can either import the functions by name, right? I just imported everything from that file, right? Which, yeah, it's just fine. Put an asterisk, right? So if you want to import everything from some library or for some file, you give it an asterisk. And if you want to only import some things, you could name them. Okay. Now from Matplotlib, that's where we're going to do some plotting from there. Not in this example, but I just put it in all of them. We can ignore that for now. So we set x to be we give it an array of 10 elements from 0 to pi. If you're from MATLAB, you've heard of anonymous functions. If you're from any other language, they're called lambda functions. All right, there's maybe a better name for it. I don't know. There may be a difference. I don't see a difference. I think it's the same thing. If I'm wrong, someone correct me. But for all intents and purposes, you can pass them the functions and whatnot. It's the same thing. I think it's a synonym. If we have some function f, this is going to give us our initial condition. So again, in MATLAB, you may see you would say f equals at arroba some variables, and then you would define it. Here you're going to say lambda, name the variables, and then this is the function. This f, I copied the wrong one here. We don't really need this. We can ignore that for now. Okay, we can change these capital F's to lowercase f's. I'm sorry about that. We set our initial time t0 to be 0 because we're starting at time 0. We can start whenever we wanted, but we might as well start at time 0. And we need to know what dx is. It's x1 minus x0. Our r is, does anybody remember? R is equal to dt over dx squared, right? Okay. All right. For this method, now these methods have different, this r can have different values. depending on the method and depending on, for the forward Euler method, this R can be as high as 0.5. Anything 0.5 or below will work. Okay. I set it to 0.49. You can set it to 0.5. You can set it to 0.12. You can't set it to 0. It has to be positive. Okay, now again, so dt is r times dx squared. That's because divide both sides by dx squared. R is dt over dx squared. So dt is, so, yeah, we need this here to make sure we get the proper time step here. The mouse cursor's there. And r is dt over dx squared. So if we multiply the dx squared, we get it over here. And that'll give us our step size, our dt step size. Okay, and then now we're going to set up our initial condition. It's going to be f at time 0, and x is the sampling of points in our bar. And we're going to set u to be u naught. And we're going to let our time be our time naught. Okay, now, this is going to be the last real hurdle here in understanding this thing. Matplotlib, I guess, has a more object-oriented feel to it than MATLAB. It doesn't have to have that. You could make this very similar to MATLAB if you wanted to. But I just took this approach because this is good to know. You have to set up some figure. And then you're going to have some axes. These are your axes. And so whenever you want to make a Matplotlib figure, you're going to need a figure. And you're going to need some axes. The figure is going to be like where you're going to put everything. And your axes are going to store it's going to store your axes. It's going to store your line. It's going to store your colors and whatnot. Okay. It's going to store your titles. Okay. So we're going to make some figure. Then we're going to make some axes. We're going to set our x limits 0 to pi, our y limits 2 to 3. Give ourselves a title. Called it, that should be 1D test. I was, color of the title is black. You can change that to whatever you like. Background color, you can make that whatever you like within reason. There may not be fuchsia or something. X label is x. And our y label is just the temperature, uxt. Now we're going to set up our line. It's going to be blank. There's nothing in the line yet. Okay. And now we can start plotting it. Now I just happened to loop this 100 times. Okay. Yeah, so this is the last hurdle here to really understanding this. It's really not a big deal. We're gonna call this function 100 times. So we're gonna take 100 time steps. Okay. So I wanted to make an animation, right? You wanted to see an animation, right? We all wanted to see this, right? Otherwise, I don't know. Yeah. I wanted to see it, okay? And so did you. So we'll just accept that, right? So we could, as we saw before, there was this loop inside the code. So we could pass some number of times here. We could give 100 here, and this would solve it for us. It would give us back u in time, and it would give us the value of u at time t plus 100 steps, right? That's what the code did. There was a for loop in there that would do that. But we're going to just step once every time inside this function. We're going to call this function 100 times, right? Because we want a picture of it at every step. If we just pass it in here, we won't get a picture of it. It'll just do the integration and just give us an answer. But we want to take a snapshot of the solution at every time step so we get a cool animation. Okay. So again, so this number of times here, we don't need this for loop here. We could just pass it a number of times there and it would just solve it for us. But again, just to make an animation, we're just going to do this once, update u, set the data in our line, save an image of it, and then go again. Update the data in the line, save an image of it, and then do it again. Update the data in the line, save an image, and then keep doing this, okay? And then, in the end, I'll show you. Let's see. What is the name of this? Okay. Just let this run. So for this one, all right. animation method 1. This is like the only way I knew when I came to Python, was to save a bunch of image files and then use ImageMagick to glue them all together. And that's pretty cool because you get a nice like GIF image, which you could save and put it on your website or something like that, or post it on Reddit or something like that. So this is just going to run and it's going to save. So I don't know, is that interesting to anybody? Does anybody use ImageMagick? Are you all familiar with that? I mean, it's pretty cool. It's like, so I just ran this. If you look here, I checked in my directory here, and there were only those files there. And then now I can check what's in there now, and now look, I got all these images, okay? And now I can just convert these to we'll just convert all of these to some image called Euler, okay? So that's all it is. You download something called ImageMagick, right? If you haven't heard of it, it's super cool, right? You take a bunch of like JPEGs or something and you can glue them together, right? I think it's neat, right? And so do lots of people, right? All you gotta do is you type convert, wildcard, Euler.gif. And then it's gonna give us a nice, yeah, we look here, we have all these images here, and it's gonna take only a couple seconds. And then we can get rid of all of these things because we don't need them anymore. Okay, and now they're all gone. And now, oh wait, don't look. Anyway, with all this talking, right, we kept the boundary conditions constant, right? Let's just see if we kept the boundary conditions constant, right? We heated it up, right? Throughout the bar it was hot, right? But we kept the boundaries at some cooler temperature. I didn't say they were cooler, they could have been hotter. It just happens that the function that we used made the boundaries cooler than the rest of the pipe, right? So the initial temperature distribution was like cold on the ends, then it gets hot, and then in the middle it's burning hot, right? And then it cools down when you go to the other end, right? So this is the image we should see, right? If you're envisioning this pipe, we heated it up, it's insulated all along length, at the ends it's cold, but we heated it up. Here's what we did, we heated up the pipe, right? We covered it in some kind of, I don't know what you use to insulate it, right? And then on the ends we put igloos on them or something, right? So it's very cold on the ends, it's very hot. As you go closer to the middle, it's hotter. We let this thing sit overnight. When we go back in the morning, what happens? It's all cold, right? Yeah, naturally enough, right? It's really not that big a deal, right? That's what you expect. But hopefully our solution confirms that. And it does. Okay. Started out hot, and it flattens out. Okay. And then we'll go again. Okay. Now, we'll look at one more way of doing an animation. Alternatively, Matplotlib has an animation function built in. Okay, so if you don't like that, you don't have ImageMagick, all you have is Matplotlib. We can set up our plot the same way. We give it a figure, we give it some axes, title, X label, Y label, all that stuff, right? We set up our line, let the line blank. I just threw in a time label here so you can see the time that was passing also, so that's pretty cool. You can put a time label, any label you want. You can put some text or a number or something on your plot, right? And then you can give the coordinates of its location. There are different transforms here. This transform, and this may be a lot to take in at once, but if you were to just copy, I think a lot of people use this. If you look at demos and whatnot online, this is pretty common. This just gives you, this makes your plot go from 0 to 1 and 0 to 1, and then you can just pick with those coordinates where you want it to be. So in this layer, this parameterizes your image from 0 to 1 and 0 to 1. And I just plotted the text at 0.5 and 0.9, so it should be, if this was our image, it should be at 0.5x and 0.9y up in the top left corner. All right, and again, we're going to make some initialization function. This is going to set up our plot area. It's going to give us the background for our animation. And then we're just going to this is going to be our update here. Every time we update, we're going to update however many times we want to the plot. The same thing, number of times with 1, we're going to set u in time equal to this. It's essentially the same thing, right? Okay, so taking a step back, Matplotlib has an animation function called func animation. You have to give it an update and you have to give it an initialization function. The initialization function just sets up the background of your plot and sets up how it's going to look between steps. And update is going to update your image for each step. Okay? And then we pass it here to the heat animation. There are some other options. The number of times you want to run it. Interval will say how long the pause between plots. Lit equals true is pretty cool because it doesn't redraw things that have stayed the same, so it makes it a bit faster. And repeat equals false. I got to put this in the documentation a couple weeks ago. It wasn't on the Matplotlib website, so I don't know. I never changed anything there, but I just wrote them. And then you can show your animation. So also there's this other function here, just not a big deal. This compares your final solution, your numerical solution, to the actual solution, which is governed by that F that we made before. I compared it, and just look at that, and you will see that we did well. Again, we should expect the same thing. It starts out hot, cools down, and then we check to see how close we were, and we were pretty close to the actual solution. Right? And as we increase the number of data points in there, oh yeah, this number is the absolute value, the biggest absolute value of the difference between our numerical solution and the actual solution, and it's not bad. It's not. And we can increase this as we increase the number of sample points inside our bar. Okay. So now I'm going to. So I think now we could maybe take a 5-minute break, and then after this time, I'm going to send you all, in this next 5 minutes, I'm going to send you all this code, and then we're going to update it. So now this code only took a constant boundary condition. So now I would like you to change it. That takes a function on the boundary. Because again, the boundary doesn't have to be fixed. We could have some thermostat on the ends, right? And we could mess with the temperature at the endpoints, right? So all we're going to need to do is change that boundary condition vector that we had. Okay. I put this here because what's his name, Strostrup from C++, he always puts puppies in his talks to help him calm down and make sure that he said everything he needs to say. So I thought I'd do the same thing. We saw how to make the animation GIF. We saw how to make this thing work with constant boundary conditions. We looked at Matplotlib briefly. We talked a little bit about the parameters for func animation. So there's these tutorials for Matplotlib on YouTube. Again, today's not sufficient, right? You're not going to leave here being an expert in this, right? Naturally. And there are some very good YouTube tutorials, right? Or if you look for Anatomy of Matplotlib, it's amazing, and it's like 6 hours or something like that. It's great. The Matplotlib website's also very good. There's a guy named Jake Vanderplas who does a lot of work with this, and he does really cool plots. And he has lots of sample plots online which you can look at that are inspiring. Lambda functions, those are like anonymous functions, and we looked at diagonal arrays. Okay. I think maybe one more thing is worth mentioning before we take a break here. I meant to hit that before. That's I'd just like to compare sparse matrices, and yeah, we didn't talk about this yet. I apologize. That was all done. That code was done with numpy arrays, which are okay, right? They're pretty good. They worked. And if you look on the numpy website, there's a section, a whole page that says, should I use arrays or matrices? And it says short answer, use arrays, right? And then it says long answer, and it goes to bash the matrices for a while. It says they're not tested enough and what have you. But parts of them are working quite well, right? And I think that you ought not to be discouraged from them. With these numerical methods, you oftentimes want a sparse matrix. because we saw these arrays were filled with zeros, right? So there were a lot of multiplications of 0 going on in there that we ought not to have done. That was a waste of time, right? So scipy has really great sparse matrices. They have like 10 different flavors of sparse matrix, right? That you should play with and get comfortable with, right? I'd just like to show you the difference in the runtime between them. I was going to go over this, but I will not. I'll just send you this function as well, but I'll just show you the difference for now, the difference between them. I just want to convince you that these sparse matrices are great, right? They're very good. If we set this size of our matrix to be a 10 by 10 matrix and then compare them, I mean, in this case, the array product looks better. It's faster. Right? This is times 10 to the minus 5. The array multiplication is much faster. This is just multiplying that diagonal matrix that we saw before by some random vector. The array time is better than the sparse matrix time, which might be discouraging, but I mean these things weren't meant for 10 by 10 matrices though, right? These were meant for million by, well, not million by million, but we're talking thousands, tens of thousands. I'm sure that depends on your architecture or something as well, what you can handle. I don't think my computer can handle 10,000 by 10,000. Okay, now we look at this. I made the number of the matrix bigger. Now it's 1,000 by 1,000 matrix. Try the same product, and the sparse is so much faster. Okay. And this is important because we're doing this integration step. We're doing it many times, right? We're looping over this Euler. We're using this function many times. There's lots of matrices being multiplied. So I suggest using sparse matrices instead of numpy arrays. And are the products equal? I mean, they are equal. Just wanted to convince you of that because you might wonder. You can't really check that by eye, right? But they are equal. NumPy has a. I'm just going to send you this. There are a number of cool functions in this script. NumPy has a way of checking if two arrays are equal. It's just array equal from NumPy. Right? It's great. Yeah. So in this script, you will find how to make a sparse matrix using only one of the flavors. This one's called SP diags. Okay. And the tridiagonal matrix. This one's using arrays, and this is using just the function that we made before. Okay. So I'm going to send this to you, and then yeah. So I would like to see if you could, if you're able to change that script to include function boundaries instead of constant boundaries, and then also if you would be able to change that. The easiest, probably the path of least resistance, the lowest hanging fruit is to change that product from being a product of arrays to being a product of a sparse matrix and a vector and an array. So that's it. So try to. We're going to take a break now, but when we come. So I mean, I sent you the script that uses sparse matrices. So in there you'll find how to, like, which libraries you need for them. And this is, again, like only one type. That's only the SP diag matrix, right? I mean, and also there are the two scripts, the one that runs the code and the other one that has the actual function in it. So I guess now I was just thinking that we just work on these and make sure that everything was clear, how to use it, what to import, how to pass these functions around to the code. Right? Do you have any questions or anything?
Are you also going to do it on the side of your own computer?
I have it ready to go. I could just show you, but I mean I figured it's an interesting exercise to do So I mean essentially for this one to make your boundary condition fluctuate, you need to pick a different domain, because the domain that we've picked is from 0 to pi. But if you look at the function f, it's like e to the negative t times sine or something. But sine of 0 is 0 and sine of pi is 0. So your boundary conditions are going to fluctuate. So one way of dealing with that is to change your domain from negative pi over 2 to pi over 2. So well, sign's not going to change, but the e to the negative t will change. So if you look in the function in the file that has the function that makes the initial condition, the f equals lambda xt, right? I mean, if are you interested in working on this? Is that too much work? You think? I don't. Oh, really?
Yeah.
Oh, so that's what I'm saying. This is great. I mean, if you're interested, this is a great exercise, like, to get going, you know? Oh, all right.
Do you say you're multiplying by e to the t or
negative t.
it or
Just negative t. Yeah. Yeah. Yes. Yeah, so I guess. I mean, are you interested in this?
Yeah.
Yeah. Yeah. Great. Okay. Yeah, so to change the array T to a sparse matrix, I guess in that function that make tridiagonal matrix, that's where you would change it. Would be in there. Just instead of using a sum of diagonal arrays, change that to one diagonal matrix. And I don't know if you noticed it in that. I mean, do you use this a lot? Have you ever used?
I've used, I was a mechanical engineer to heat transfer 20 years ago.
All right.
And,
Right.
and I use Python. I mean, I'm familiar with numpy, scipy. I use this stuff to some degree.
Okay.
So some of this is like somewhat current for me, like the actual Python part. Some of this, like I can get the transfer aspect.
Yeah. Yeah. So I guess this is the way that I made this sparse matrix. I mean, I would suggest just copy and paste that, because there are like, I think the only part that's like frustrating with scipy, maybe a little bit, is that there are like 10 million ways to do something sometimes, and like to make this. I mean, this is just the way I do it. I just make this is just an arbitrary sparse diagonal matrix. It just has, do you know this A range? It just gives you 0 to however long, right? And VStack, VStack is like, it's pretty cool. I had trouble with this. I couldn't get this thing to work forever because there's a VStack in numpy and a VStack in scipy. And when I read the scipy book a long time ago, I remember seeing that, but I had imported from numpy just everything. And then it was screwing up because it was using the wrong one. So you have to make sure that you import the scipy VStack. But what it does is it takes 3 arrays, however many arrays you want. You give it a tuple, and it stacks it just stacks them vertically on top of each other. So it's just going to stack. If you can put a print under there, if you have the script, put a print below data and print it out so you could see. The offsets is pretty clear what it is, right? It's just the 0 offsets the main diagonal. The 0 offsets the main diagonal. Offset 1 is super -1. It's below. I mean, you're really good at this, right? Like you've done this before, right? Are you interested in this? Or have you done this before? Are you familiar with all this stuff?
Yeah.
Yeah, right. In Python?
Yes.
Yeah, right. Okay. So with yeah.
Function there, could you do arbitrary offsets?
Yeah, up to I don't know if you could put them out of range. We could try that. We could try and put it like, you know.
So if I say I have all ones down the main diagonal and then I skip one diagonal is all zeros and then do the next one.
Oh yeah, you could totally do that. Yeah, like here, you could change this from -1 to like -2, and then we could like print out the matrix A. Okay.
Current Python build doesn't have scipy, so I'm installing it right now.
Oh yeah, so like that Anaconda is great, man. Like you know.
Anaconda, this current environment is actually probably the work environment, so we're not on Anaconda yet.
Oh yeah, right.
And so I can't help you with it too much.
Oh yeah, but you can. Oh, also if you want to, this stores them in like a sparse format, so it won't. You have to print. You have to do like it has 2 dents. You have to print it as a dense matrix. Otherwise, it'll print out some like doesn't look nice. Like I don't know, like CD. That's on the desktop. Oh, that's too big. Let's make it smaller. Yeah, you see, you can space it out. And I want, yeah. Also, the cool thing is like with arrays, like with these sparse arrays, you notice like the data is the same. It's the same array. It's the A range of length size, right? In here, and then we just stack them on top of each other. But if you look here, like this goes from 0 to 9, and this one goes from like 1 to 9. Like it throws that 0 away because it doesn't fit in there. But if you use a diagonal array, though, you have to make sure that fits in there, right? And then if you put like -1, it'll throw away the 9 because the 9 would have been down there. So here it throws away the 8 and the 9. Right. That's cool. Yeah. Yeah. And these products return arrays also. They don't return like matrices. They return numpy arrays.
Is there like a 2-minute explanation of how this sparsifier operation works, like how it sparsifies the matrix?
I don't know about it. I mean that's like, I thought that was like a quantum leap in computer science when they could do that. I don't know how it works. Do you know? I don't know how sparse matrix somehow.
I'll look it up.
Yeah, I'm sure it's like.
So I'm kind of at the starting line now.
Okay. All right. Great.
I'm actually going to just run this and see if it actually.
Yeah. Yeah.
So I'm at the starting line where your code seems to run so far.
Do you get the animation? Do you have Matplotlib installed?
I do.
All right. You don't have your laptop, man.
So I missed that. Which one? I ran test parse that worked. So I'm not
Yeah.
sure
Okay.
test parse.
So,
Now, do I need the that other way of gluing the
No.
PNGs together?
no, if you want that to have it, I mean,
Mine.
yeah, yeah. I feel like that's kind of like Stone Age stuff or something. I don't know, but it's cool. I like it. You can save these animations. You can save them, but you need to install like something called like FFmpeg or something like that.
It's okay. I don't
Yeah, but
I'm gonna just run this.
matter of fact, what's your name?
Mike.
Mike. Oh yeah.
Yep.
All right. I can send you everything I have actually.
Yeah, the single graph array worked.
Yeah, that's good. No, wait, everything. Come on, man. Oh, wait. Maybe I gotta zip this or something.
Zip it all.
Yeah, I've never done that before. What, you just zip, right? Just.
Yeah, just go to like your file browser.
Oh, yeah?
It's probably the easiest way to do it. And then you can just right click and press. Yeah.
Compress.
It's the second one.
Yeah, thanks.
You can pick whether you want it to be a tar ball or a
What do you like?
Yeah,
Zip.
zip's fine, yeah.
Okay, that's good. Thanks. Okay. I mean, it was only like 10 megabytes with everything. I think this you can send. What was that?
In theory, would it be feasible to do the type of stuff you just did here with numpy directly to do that with pandas, or is that not a job?
I've never, I don't know, I don't know, I never used pandas. I heard the book I had on it said statistical analysis. I closed it because I said, I don't need to do that. You know, whatever. But I heard it's great, and there was like a tutorial today on it or something, right? Or talk. I meant to go to it, but I couldn't make it on time. Oh, send.
Go back to your presentation for a second.
Yeah. This.
That, yeah.
Yeah. There you go. Yeah. The easiest thing to do is make a sparse matrix instead of a. This is ugly. I'm sorry. It's ugly. I was trying to fit it, and then it kept.
No, that's fine. I import library from sparse matrices, so.
Yeah. So you can check that test sparse file, and that would show you which library if you wanted to use that. And there, if you look on the SciPy website, you'll see this.
So what
Yeah.
we want to do is take the heat presentation file and modify it.
Yeah, exactly right. Or I guess the sparse matrix would need to go in the other one, in the file that has the actual integrator in it. That make tridiagonal matrix. Should switch that.
Should I just save a separate copy of that, at least I don't have to back to
Yeah. Right.
I'm getting a attribute error. Just running it without changing anything. Like right, I don't.
Attribute figure canvas has no copy from the box.
So that is.
You haven't changed
that's just
anything?
in the.
I mean, you saw it work, right?
Right.
It definitely works. It could be. Do you have?
in this Matplotlib?
Yeah, it could be. I mean,
I don't.
I'm using
it
one.
says Mac. Are you using?
No.
Yeah, so it might be something weird, Mac specific.
Yeah, it could.
Isn't- That's kind of interesting.
But yeah, you know what though? I ran this in the on a Mac
yeah,
a couple days ago, and it ran. But it could be the version you have or something. You know what is it like __ version or something like that in Python? I think you just fire Python and you import Matplotlib. I think, or it's like dot. It's like underscore. Yeah.
Oh.
Yeah. Yeah, one. That's what I have too. Yeah, that's strange. I don't know. Can you get PyPy running on an iPad?
I wish.
Or can you get like a? Yeah. Yeah, that's strange. Do you have like a VM or something on it you can use? I guess. I guess in like 15 minutes, we'll look at the solution if we don't have it yet, right? It's 5:30 now. It's 5:45. We'll just look at the answer, right?
So why don't we just start with number one?
Yeah, definitely 0 and 1 should be accessible.
Yeah, so.
I don't know. I'm curious about that. I don't.
Yeah, I'm not sure even where it's.
You did everything.
It seems like it's looping, so it's just trying to generate each picture.
Yeah. Do you want? You could just
Failing.
get rid of the animation, right? That's what the issue is, right?
Or just flash show.
I don't know. Yeah, I don't know. Yeah, good.
So not show, does it show?
Close that. Oh, but you know what?
So,
I could send you I could send you everything also that has the one that. Oh, that's good.
so Charles the first. That time.
Look, what's your name? I'll send you the other files as well. Andrew, all right? Yeah, because then. Right.
How many items are there?
Oh, Kubera?
Yeah, Kubera, that one.
All right. Thank you for that. Attachments.
Send a copy to me at
Yeah.
Riley.499.
That was you?
Yeah.
All right. What do you do here? Are you
Grad student.
in math?
Aerospace.
That's cool. Yeah, that's cool. Yeah. I had a friend from aerospace or whatever, a guy in one of my classes. I forget what his name was, but he did something with like got some award from NASA or something like last year. He was bald and probably like Middle Eastern or something. You know, I don't know.
You know what the award was?
I don't know. Well, you guys are like a stellar department though, right? So probably awards all over. Wait.
R-I-L-E-Y, sorry.
RY?
R-I-L-E-Y.
Okay. Dot 499. That's cool. Oh no. Scipy stuff.
And this has that sparse matrix.
Everything in it. Everything in it. Everything in it. They're really good. I wanted to bring some files on how to use like some C++ functions also, but then I didn't have time to.
Your comma there. Otherwise you
Oh gosh. Thanks, man. This one,
might have some trouble with that.
right? What the heck?
Microsoft is part of that.
Riley.499 dot edu. Dang it. That's good. Okay. Yeah.
So you're computer science or
Math or computational science, like on the frontier, I guess. So hopefully right on the boundary. This thing to make the GIF image was a pain in the neck to figure out how to do this part in Python to like print out the files and with numbers like from 000 to 001 to 0. I don't know. Maybe a smarter person could have done it in a minute, but it took me like hours to figure out how to do that. That's too bad, man. I thought you were going to bring your laptop. I thought this would be a great introduction to Python for you, you know? No, no, I had a really theoretical thing in there, but then talked all about random walks and stuff like that. But then I gave this a few weeks ago in the lab where I'm working, and he was like, "No, throw that away." He said, "Either everybody's gonna fall asleep or they're gonna already know it. Like the folks that would know it already know it, and the folks that don't know it probably don't want to hear it." Yeah. I mean, that's great. That's great. All right. Yeah. Did you get that going? Oh, no. Yeah, right. That's fine. Yeah, the answer is there. It's in the Sparse folder. Yeah.
I was able to run the stuff you gave us.
Yeah.
Successfully.
Okay. All right. I guess we could just, we'll just run through it, I guess, quickly, make sure it makes sense. Is yours working yet? I don't know. I don't know, it could be, did you like install everything like from command line or something?
Yeah.
How'd you do that, right?
Oh, yeah.
Piece by piece or something? Yeah, I don't know. Like both of those, they have, like everything's built in, like they have their own like virtual environments and their own versions of like pip and stuff in them.
Yeah.
And they're so,
Did you have to make one reinstall or pip install? Well, I don't know, skip play and see.
what are you looking for?
Matplotlib.
Oh yeah, all that comes with it. Yeah, it's great. And yeah, it's, yeah.
What's your background?
I guess I'm studying computational science. So I'm doing like, my thesis is on modeling the growth of epithelial tissues. Like we have like a mesh of tissues, of cells that's pretty cool. The cells divide and stuff, and some of them die and whatnot, and then new ones grow and whatever. It's pretty neat.
It's Conway's Game of Life.
Yeah, I don't know what that is, so I'll just say, what is Conway's Game of Life?
It's they run it up in one of the other talks, but it's essentially this simple little algorithm that you have a grid of cells that you start off with.
Yeah.
There are certain rules that if you have, say, a cell that's on its own, it will die off.
Yeah.
If you have too many cells in a certain area connecting to each other, then they'll also die off. So it's the game of
That's
life
cool.
is if you're too clustered or too dispersed.
It's not good.
But then it's interesting.
Yeah.
YouTube, there's a million videos.
Conway's Game of Life. Conway's.
It's actually really cool. If you have free time to play into it, you can find little actions online where you like select what you want your starting position to be.
Yeah.
And then you can watch it all fall apart.
That sounds good.
Generally speaking, if you make like a random thing, it's not going to be stable and then they all die. But there's some pretty cool ones where people have made sophisticated things that like make these sort of rocket ship looking things that will attack other things and make them that. It's quite interesting.
Awesome. John Conway.
I think Wikipedia has a little animation if you want to.
I don't get it. Those things crashing into each other? I have to read it. Oh, that's cool. Who was talking about this?
It was during the Shape Lady.
Oh, right.
talk.
What's it? Her name's Alvarez, right? Allison? Is that what it is? Yeah. What was that called? All right, so I guess we're winding down, right? We're almost out of time. I mean, it's your thing running out now, right? I mean, yeah. Yeah, it's finicky, right? I mean, I don't know why it's not working. Yeah, I guess I feel we just run through. I don't know. Do you want to look at the code with the function boundary, maybe? Did you? I mean, are you looking at that? Or are you still toying with it?
Good. I've been actually trying to
Okay, yeah, so, I mean, I guess this is what it should look like. So, well, this other one, I gave it, like, you can give it, like, complicated functions on the boundary. I used the same function that we had, but our function was e to the negative t times sine of x. I think that was all.
The result is if you were fluctuating boundary temperatures over time.
Yeah, yeah. This one's dependent on time. Otherwise, it wouldn't change. Because the x wouldn't change, so the y needs to change. Yeah. So we have this. I just gave it a +2 because I didn't want a 0 boundary condition. If there was I put +2 here just to make sure everything was working, because if it was plus nothing, this function's 0 on the boundary 0 pi, and then in here in the function, these boundary conditions would be 0, and then you'd just be adding a 0 there, so you wouldn't know if it worked or not. So I just gave it a +2 to make sure that it was working as well. But this one, now we changed our domain from negative pi over 2 to pi over 2. So, you know, sine pi over 2, negative pi over 2. It's like, yeah, it's 1 and -1. So we should be able to kind of guess what this should look like. This is going to see staying. It shouldn't move too much, right? This is going to stay at 1 or -1. But this is going to get small, right? As time goes on, e to the negative t is going to get small. So our curve should be like kind of like something like that, and then these two should just kind of tend towards 2, because that other part's going to go to 0. So just so you see that it works. I don't know if on Python, what is this called? Function presentation. That's what it does. Right? So hopefully it does that on yours. Right?
Which one is that?
This is in the function BC folder, I think I called it, for boundary condition. Where's that?
Slow it down.
Yeah, you can. Yeah, do you remember? Any remember?
Like a 0.03, and then you just change that, right? You have the gap in there.
Where?
Or so you have the interval somewhere.
Yeah, right here. There's an interval parameter for func animation. We can make that like 100 if we want. It doesn't. We'll make it something bigger. We'll slow it down a bit. So that's good. Mm-hmm.
Okay, which file is this again? Where?
This is gonna.
See?
Yeah.
This is function presentation inside of
Yeah, that's it. Yeah. Yeah, this one I couldn't. It wasn't clear on the website for the longest time. I've been using this animation for like a year now, and I didn't know how to make it stop. And on the website, it never said that there was a parameter called repeat. I happened to come across a repeat somewhere on some code sample online. Yeah, so you can make this repeat false. If you make it true, it'll just go on forever.
So what you're looking at when you run this one, and it gives you the white background with the blue line, is the same image. You're just refreshing that image over and over again.
Yeah, exactly.
Whereas the other one is actually an animated GIF where you're
Yeah, it's a bunch of bunch of images glued together. Yeah, and this one, it has this blit parameter also. The blit doesn't. It means that the stuff that doesn't need to be redrawn isn't redrawn. So if you turn the blit off, this thing should, I don't know how much slower it'll get, but, because a lot of this, almost the whole plot is changing, I guess, but I don't know. A lot of stuff is changing. I don't know if it would make a difference. Well, you can't see it with that. But I don't know. You could time it. You could time it somehow and see. It does give you some improvement.
Is there a tool to export that or save that animation?
Yeah. No, you have to have. You have to have either. There's two things. I know one of them's FFmpeg, and the other one's like mem encode or something like that. I don't know. You could look it up. There's nothing like in Python to do it. There's you could. Yeah, there is a way, but you need to install some other stuff. In fact, this guy Jake Vanderplas, I met him like a few weeks ago. He's great, man. I like this guy. Really smart, and his he has like a cool blog called Pythonic Perambulations. He puts like cool like code he's been working on. In here, what he had here. This is here. I don't know if this works on mine. We could try this. Yeah. We could try this. give it a shot. And should have sped this up. Let's see now. No. It's not there, right? I don't know. There is a way. I don't know how. Yeah. Okay, I guess, what do we got left? 15 minutes? You want to see the 2D code? Yeah, it's, the 2D code is kind of like diabolical and a little bit hairy. But it's pretty much the same thing. The 2D one is like if we have a... I didn't even put an animation for this because I was sure we wouldn't make it to that, but sure enough we didn't even make it to the... The animation works the same way though as this. You can use the animation function. Just look at this also, and just as a in conclusion, it's like the same problem. This one's like 2D, like you have a plate. I put a picture of a Sicilian pie in there, right? Like you had a pie or something, and whatever. You want to see how the heat changes in that? This is like a really simple domain. It's just a square, but I mean, you could make it more complicated, I guess, if you wanted to. Same thing. It's got like it's heat. It's cooled around the edges and hot in the middle, so it should be like a gumdrop or something, right? That's what you'd expect. And then if you run it long enough, it should get flat. All right. So this was like I didn't put the animation. I just plotted the solution. But the animation's like the same. But this is like flat at 2 after some time. But, and if you wanted to run it for less time, you could just change the final time to something smaller. That's too big even. No, that's still too big. It's still flat.
Like, what is the starting point here? Is it the same temperature
This one?
on all the edges, and then in the middle is something else?
If you want, yeah, we could. This is like here we use.
That I read, it looks like a taco.
Looks like a taco. Oh my.
Maybe I'm misinterpreting what I'm looking at. Yeah.
Yeah.
Yeah. The high ends here.
That one has a function on the boundary condition. If you change the time for that, it should flatten out. Yeah. Yeah. So if you change the final time to something bigger. Yeah. Yeah. So, yeah, but initially it should be like this, like right, like a big hump. Yeah. So. In 2D, I don't know if you use Matlab. I don't know. It's got all the same in 2D. You got all the same stuff as you have in Matlab. You got like a mesh grid. You just got linspace. You can still. You just have to make sure your plot is 3D now. I guess you have to make sure that your axes have this 3D in it instead of 2D.
If you want to see the graph, what you vary here?
Which one are you looking at?
I'm looking at the same one you were.
The 2D constant boundary condition presentation. Just change this number of times here to run it. Yeah. 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 And if you want this to be smoother, you can change this number here on the top.
That's just going to change the amount of squares.
Yeah, right.
Instead of 5 by 5, you end up with.
Yeah, exactly right. Yeah. So we can make this, exactly. Yeah, we can make this like 50 and make this like 10. And also, this has these plots here. They have this anti-aliasing also that makes your image look a little nicer. You can turn it. I turned it off. You can turn it on if you want. False, true, false. You can change your line width. You can change it to something silly like 20.
And if you wanted to, we could throw the 1D little thing that made the animated into this.
Yeah. Yeah. Right. That's too much.
Is that too trivial?
That turns the line width way too big. Yeah.
50 words,
Yeah. Right. So you can change your color maps here too for your plots. You have this here your C map here in your plot. There's nice ones like autumn's pretty nice. There's like autumn. There's like winter. There's some green ones. All different types. This has too many lines on it. Maybe that's one. Yeah. So that one looks nice. Also, I guess pretty much done here, but there's also these cool functions here for 2D arrays. Like numpy has a subtract function for subtracting arrays, which is useful. You can take this absolute function, gives you absolute value in an array. Amax will give you the max in an array. So. Any other questions? Anything to do with it? So, this is perhaps a bit too complicated. Perhaps a complicated project for an hour and a half. Right? I think, have we accomplished our objectives though? The objectives setting out here were to know what the heat equation is. We all know that, right? Right?
Yes.
Yeah, good, right? We know how to solve it in Python?
Yes.
We've seen that, right? Have you learned something about some of these libraries?
Yes.
Right, good. Do we make animations? We did, right? So that's perfect, right? Yeah. Yeah. Right. Right. Yeah. So, great. Great. Yeah. Thank you. Yeah. Great.